the uncharacteristic jacket. Now, if you've seen it, I'll take it off. I see I've already made a mistake. My name is bigger than MIT, which is clearly undesirable. Thank you for coming. Thank you, Peter and Louis, for inviting me. The work that I'm going to describe, it is not my work. It's a work of a considerable research group who I'd like to introduce: Steve Crouch-Baker, Nada Jessic, who's just joined us, Stuart Smedley, Brent Kenzeller, Mark Williams, and Sharon Wing, the group of people currently working on this project. Arthur Schreiber and Romeo Rocha have left the project and gone other places, and Andy Riley was killed on January the 2nd of this year. Funding is provided, very gratefully acknowledged, by the Electric Power Research Institute. And in addition to funding, the Electric Power Research Institute has provided considerable technical contributions to this project in the person of Tom Passel, Joe Santucci, and Bob Weaver.
Mark, about 3 dB more.
There seems to be an electrical fault with the microphone, but I can't show. I'm just going to give you a little overview of what I hope to present here, and I have a tremendous amount of information.
Could you try a little fine focusing?
Is the lights down too?
Complaints. How's that? As we're going through these iterations, the announcement by Sandplant and Martin Fleischmann in March of 1989 took us all by surprise. Some were more stunned than others. As it happens, I have been working on the hydrogen palladium deuterium palladium system for about 13 years at that stage, and it occurred to us at that stage that in order for anything that was being claimed by Fleischmann and Pons and by Jones about the deuterium palladium system to be true, it had to be true under extraordinary circumstances of that system. And our hypothesis, the hypothesis that we set out to test experimentally, was that in order to produce this anomalous effect, or any anomalous effect in the system, it had to be done at very high deuterium to palladium ratios, very high loadings, as we will describe them. This is a circumstance under which the DPD system is not well studied, has not been well studied, and anomalies potentially could occur. We embarked upon an experimental program at SRI to test this hypothesis, and our experimental program was really determined by an attempt to understand this explanation, not an attempt at replication. Because we didn't study newspaper articles to try and find out what the geometry of the Fleischmann-Pons cell might be. We simply took the idea that if the deuterium palladium system was producing this anomalous effect, and if this anomalous effect would be produced at very high loadings, what would we do to produce a highly loaded system and examine the system for anomalies? Our experiments were based upon our own experience. That is, we used our experience in creating high loadings and monitoring the loading of the deuterium palladium system using resistance ratio and AC impedance methods in order to establish this experimental program. And the idea was that we would obtain scientifically useful results, whether or not replication was successful. What we know today, and what I hope to lead you to towards the end of the lecture, is that we can demonstrate that there is, under special circumstances, a substantially larger energy out in the experiments as determined by calorimetry than there is known sources of energy put into the experiment. Obviously, and consequentially, the output power under special circumstances is larger than the input power, and I will assert, and not have time to demonstrate fully here, that that excess power is larger than the measurement uncertainty by numbers like 20 sigma, 30 sigma. There is a very strong observed correlation between the excess power and the deuterium to palladium loading as determined by the resistance ratio. We do not see, have not seen, quantitative nuclear products. And the condition that we're at now in our understanding of this anomaly is that the effect is either real or it's some obscure artifact, and perhaps an artifact that must change from experiment to experiment. The observations that we make are larger by at least 2 orders of magnitude than the known chemistry of the contents of the electrochemical cells. Our experiments were divided into 3 groups, and I'm really only going to concentrate on the heat results today. But in order to obtain excess heat in these experiments in our hands, one must achieve deuterium to palladium loading ratios in excess of a value of something like 0.9. So at least a third of the experiments that we have performed have been intended to address the issue of how do you get deuterium into palladium, how do you keep it there, how do you monitor it and maintain it in this high activity state for considerable periods of time. I have on this slide the experimental parameters of this set, and I'm going to describe them no further than to say that in order for us to obtain and maintain high loadings, we must form in situ on the surface of the palladium cathode in its alkaline electrolyte a film where the constituent parts of this film contain the elements either silicon or aluminium, and others may be possible. Our conclusions are somewhat at odds with some electrochemical conjectures in the last few years, but by no means at odds with the known electrochemistry of the hydrogen-palladium system in the 20s, 30s, 40s. By careful control of the electrode pretreatment, the electrolyte composition, and the current density, it is possible to attain and maintain the high loadings, deuterium to palladium ratios, approximately 1, that are necessary to produce the anomalous effect. I'm going to talk about loading quite a lot, and I'll correlate my results somewhat with the deuterium to palladium atomic ratio. In our experiments, the primary tool for determining the loading is the resistance ratio. Here I have a plot of the resistance of a piece of palladium as hydrogen or deuterium are introduced into the atomic lattice. The resistance ratio goes through a maximum at a value of about 0.7. And these data here, the green points, are extracted from the literature of gas loading experiments by Baranowski at very high pressures, multiple gigapascals of deuterium pressure. And we infer our loadings from the measured resistance ratio. So we are requiring the resistance ratio has gone through its maximum, is on the right-hand side of the maximum, a fact that can be determined from the derivative of a parabola being more or less a straight line. If we increase the current or increase the hydrogen pressure and the resistance ratio goes down, then we can fairly easily determine that we are on the right-hand side of that maximum. So we're looking for high loadings as determined by the resistance ratio. I'll spend most of my time today on the calorimetry. We've done something like 30 experiments in an isothermal flow calorimeter. Several designs, low pressures of deuterium gas, medium pressures 1,000 psi, high pressure 10,000 psi, covering a wide range of current densities, incorporating a wide range of operational powers. And one of the key features of these experiments is that they're very long. They occupy 1,000 to 2,000 hours, 1 to 3 months. We've observed unaccounted for excess powers on 40 occasions in the 2.5 years of experimental program, in which we characterize 2 basic categories. A baseline excess, these are not our terms, and they're not the terms that I would have chosen, but they're used by the